And okay, live stream is running, but I'll give people a minute to settle. And you can put the boring stuff in first. Want me to say anything? Silent observer. You're not here. Let's start with a little bit of recap, because we finished last time in the middle of one section. So before we properly start, we discussed this problem that we didn't eventually solve yet, the longest common substring problem. Guys, discussing after. So this problem sounds like a formidable challenge. If you're given strings, you're trying to find the longest substring that occurs in any of those strings simultaneously, and you want to do this in time, essentially just needed to read all the strings. And indeed, as I mentioned, Duncan-Knuth conjectured that that's not possible, but suffix trees solve that. But you haven't seen yet how, and that will be coming up next. Then we discussed what a suffix tree is. I don't want to repeat the definition of compact tries in detail, so you have to go back if you forgot already, but that's what they look like. So the suffix tree is the compact trie of all the suffixes of a text, with this little caveat that we always add an end of word marker, the dollar symbol on the slides, to the end of the string, so that every suffix, well, that no suffix is a prefix of another suffix. That was the important bit that made life easier for tries. And that convention we used in all of these examples here. And then I showed you how to construct the suffix tree the slow way, by first inserting every suffix in a trie, a standard trie, and then compactify it. You could have gone straight to this one, but still it needs quite a lot of time. Then I want to recap that part too, because we'll need that in the algorithms. We had several ways to represent suffix trees on the slides, and they're lying to different degrees about the actual representation in the computer. This was the human version, which is the most lying one. It has the actual suffixes as strings listed in the leaves. But in reality, what each of the leaves stores is just a number, which is the starting index of that suffix in the entire string, and we store the string once and for all, somewhere on the side. The second bit where this representation is not exactly what we store is it has entire strings on the edges as labels, whereas what we really have is just the first character of each of these labels. And the internal nodes tell you what is the next position that you have to compare with. So there can be jumps if the label has length 3, for example, here, then that number goes up by 3. We've had that in detail. Just wanted to remind you, this is what you actually store, and this is what we'll work with for the algorithms. We discussed that the standard construction is very slow, but there's this magic black box that we haven't looked into, but I just promised you that it exists, that there's a way to take a text of length n and construct the suffix tree in also linear time. So theta of n time, essentially the time you need to just read the text, and afterwards you have constructed this suffix tree. We won't get to that today, but probably tomorrow. So it's not so much of a black box for much longer, but for now we'll leave it with that. And we discussed some nitty-gritty details of the definition. We've also seen a first application of suffix trees, namely the one that's asked about in this question that I had on Slido. Maybe as a warm-up, we can do that again, just to see if that's stuck. So here's that question again. And you can join. Hopefully you have for the code anyways. And I'll go back to the question here where we can see the suffix tree. So it's the same question as last time. I already discussed in detail the answers, but I thought it's useful to recap that because the second application we'll look at in a moment builds on the first one. We had 70-ish people for the attendance code. So you can see a few more votes for this one. 35. I'll wait till 50, not till everyone has voted, because we've done that one before. So I don't want to spend too much time on it again. But get those gray cells up and running again. Two more. Okay, we have 50 plus. And here's your answers. And so let me go back here. As I said, we discussed this in detail, so I don't want to go over it in full detail. But on the example here, we have the same tree on the next slide, right? So if I want to find all matches of A and A, I have to traverse with A and A. I'm ending at an internal node in this case. That means there is an occurrence. Namely, there's an occurrence at all the indices that are at leaves below this node in the subtree of that node. And in this case, that's indices 1 and 3. That's why here these two answers are correct. Of course, that also implies there's two occurrences and there's some occurrence. And then all of the other answers are wrong for some reason. Okay. So that was the first application that we've discussed in detail last time already. The string matching problem that we discussed in Unit 4 without suffix trees. But it turns out if you want, you can use a suffix tree for that. You build the suffix tree for the text, and then you traverse with the pattern down the tree. Now, in general, there's different cases that can happen. And these 5 examples illustrate all the cases. If you take A and N, you can't traverse with an N, so you fall out of the tree. That's this part, you get stuck, so the pattern does not occur in the text. Second option, BAA. Oh, I'm also falling out of the tree, but this time in the middle of an edge. So I'm in this second case here. It also means the pattern does not occur in the text. Now I might only find out in the compact try by comparing with one of the characters from the leaves. But for the human version, we can directly see it. A and A, chuk, chuk, chuk. That's the example we've had before. That has some occurrences. If I end somewhere and I run out of pattern, I can continue in the tree and find all the occurrences. BA is similar, but I'm ending in the middle of an edge. But again, I ran out of pattern and the tree continues, so I can keep reading downwards and all leaves I find are indices of occurrences. And the last one is a little subtle. So if I do in the compact try this one, I would find matches because the first character B that I check matches this B. Then I'm skipping 2 and I check the A again. So it looks like I'm traversing to this leaf 0. And in the compact try, I would only then notice that there's actually characters in between that are mismatched. In the human version, of course, you would see it earlier and you could terminate early. But these are all cases. That's all that can really happen. The last part can happen in this case where I'm skipping over characters. If this here had been very, very long, then I would try to keep going, and I run out of tree. Okay. So far, only recap. We can find a first match, some match of a pattern in time proportional to the length of the pattern. What I said last time, if I want to find all the occurrences, I have to traverse the subtree, and so I have to spend at least the time to produce all those occurrences. And this thing here, this running time of just proportional to p depends on these green edges. A small addition to the suffix tree that we can do for free in terms of big O, every internal node stores a pointer to one of the leaves below it, one of the leaves in its subtree. It doesn't matter for the running time here specifically which one we take. Here I always took the one that's leftmost according to alphabetic order to break ties arbitrarily. You could also do the one that has the smallest index. That would also be sensible. Sure. Okay, that was string matching, but we already knew how to do string matching. So let's move on to something new. Perfect timing, by the way. I've just finished the recap. We left off last time with solving string matching with suffix trees, but we already knew a solution for that. So now let's look at a new problem, and this is one step in between to this problem I took as motivation initially, this longest common substring problem. And this is the longest repeated substring, slightly different. Here we have a single text, and in this text we try to find some substring that occurs at least twice. So there's a substring in the text starting at position I of length L, and there's a second occurrence, so another starting index J, where this also occurs. Okay? The definition allows that these two overlap. That's fine. You can define variants where this is not allowed, but here we are happy with that. So in a way, a trivial brute force algorithm could just try for every I, you could try every J, and then see how long you can read. That sounds like it could even go cubic. It's very slow. And it seems that we have to at least check all possible substrings. You can do better than cubic if you check all start and end indices and check if they occur another time in the string. That's essentially string matching in disguise, so we could solve that. So quadratic time is easily doable and is still somewhat trivial, but that's still way too slow. I'm still not happy with that. All of these simple solutions seem to rely on checking every possible substring of a text, every start and end position explicitly. And as long as we're doing that, we're too slow. We have to spend quadratic time to do that. But it turns out with a suffix tree, we can avoid that. And the reason is that we don't really care about all substrings. All we care about are the repeated strings anyways. So there are, in a sense, many substrings where we can easily exclude them as not being interesting because they only occur once. And to motivate why the suffix tree helps, look at the example here from the small text that we had last time. It's a small example, so the overlap is only small. But maybe you can imagine how this generalizes. So in this word banana ban, we have two parts, a ban and an. That's two suffixes. And they both start with a. They have a common prefix. So two suffixes, and start somewhere in the word, go until the end. If they have a common prefix, that's a repeated string because it occurs at the beginning of two suffixes, so it occurs at two positions. Let me maybe draw this briefly. So I have two positions, I and J. The whole thing from here to the end, that's ti, and the whole thing from here to the end, that's tj. Now, if they have a common prefix, that means there's a substring in the text that occurs twice. Because I could put tj again here, and then I would have matches in some prefix here where these characters are the same. Okay, fine, but what does that mean in the suffix tree? Because the suffix tree is a trie of all the suffixes, there must be a path for these two suffixes as well. Namely, there's the path going to 5, and there's the path going to 7. It's the starting indices. Now, in these two paths, they are starting at the same node, namely the root, and then they end somewhere different. So at some point, they branch out from each other. So they have this shared segment here, and then they differ. And that shared segment is exactly the longest common prefix, because that's the part of the string that they share, where they are the same. And in this case, it means the suffix tree has to have such an internal node, because if they have a shared path and then they branch out, they have to branch out at something, and that's always a node. So there's an internal node that you reach with this common prefix. Now, the thing is also true in reverse. Any internal node in the suffix tree is also the common prefix of at least two suffixes, namely some leaf that is where the paths split at this node. If there were none of those, if all the leaves were in the same child, remember it's a compact trie, so then this would have been eliminated. All our nodes have at least 2 children. Why does that help us? Well, we've analyzed this earlier. The number of internal nodes in the suffix tree is at most linear. It's at most the number of suffixes. And so I only have a linear number of longest common prefixes to check at most. So even though there are many more substrings in the text, if I restrict myself to the repeated parts, there's only a linear number of them that are candidates for being this longest repeated substring. In a way, that's the magic of the suffix tree, that it nicely narrows down this list of candidates for us. All right. So to put that on the slides, what we discussed, the longest repeated substring in the text always has to be also the longest common prefix of 2 suffixes. I don't know which ones, but there's 2 indices so that this is the longest common prefix. And so as an algorithm to find the longest repeated substring is compute the suffix tree. There it is. Takes linear time by the black box construction that we haven't shown yet, but you can take my word for it. Then we compute what's called the string depth of all the nodes. And that's something that'll come up. So let me highlight that. And let's do it also here on our example. It's nothing but the length of the string that leads you to this internal node. So it's just reading along. Here I have 1 character read, so I have string depth 1. The root always has string depth 0. Here's also 1, but here's 3 because I have 3 things on the edge going down there. Here's 2 and 3, and here's another 2. Okay. Now, systematically computing those would be a search from the root. You have a recursive algorithm. If you say a recursive function that starts at the root, remembers how deep it currently is, and whenever you branch down, you just increment that depth by how long the edge label is. That's computing the string depths. So you do 1 traversal of the tree. That's linear in the size of the tree. So it's linear time in the length of the text as well. The second step is, among all those nodes, we have to find one that has a longest shared path, so it has maximal string depth. And that's also easy. You just traverse the tree a second time and keep track of the maximal number you ever see as string depth. So the maximal string depth in our example is not unique. There's 2 places. These 2 nodes both have string depth 3. And so they correspond to the strings ban or Anna. And both of those occur twice in our text. You can check this, right? Ban is here and here. And Anna is a bit more interesting. Anna is here and here. So this is an overlapping occurrence where it shares the A in the middle. As I said, that's okay. That's allowed. If you wanted to disallow those, then you have to modify the algorithm a bit. But we'll keep it with this straightforward version. So we all have a linear time algorithm. As long as we can construct the suffix tree first, the rest is all done in linear time. Now this problem already feels somewhat similar to the motivational problem. A repeated substring in one large text is similar to having this common substring in several texts. It's not exactly the same, but at least you can maybe see that there's some similarity. So maybe you can hope that a similar trick works. If you start thinking about this, maybe you could just take the texts in isolation and build the suffix tree for each. But if you play with this a bit, you kind of don't see that going anywhere. Instead, what we seem to need is somehow a single suffix tree that covers all the texts. And to motivate that, let me go back briefly again. So this correspondence that an internal node corresponds to a repeated string, right? That was because there were 2 paths going to different leaves that are shared until this point, and then they branch off. If I want to find common substrings in different texts, then I also need this kind of shared path and then branching off into different strings. And for that, we somehow need something that puts all the texts in one big tree. But it's maybe not so clear how to do that without losing the information where things come from. And so that's a second little concept. It's actually a simple trick that works. But I think it's very useful to have this one in mind. You can define a generalized suffix tree that works for several texts. And conceptually, it can be thought of as just the suffix tree for the text where you concatenate all the texts. If you also have special markers in between that tell you where each of the original strings ends. If you don't do that, then a few things break. But it's easy to add these extra special markers, a different marker for each string. And then you can use the construction for a standard suffix tree as a black box. It doesn't need to be modified. The reason for these dollars is that if you take a suffix of this concatenation of all the strings, they can be of different length. That's fine. So here's my $1, $2, $3, and so on. Because these are all new symbols that don't occur anywhere else, if I take any suffix of this, say this one, okay, don't want to run into the car. If I take any suffix like this, every suffix of this long text will have a leaf in the suffix tree, in T, the curly T. So there will be a leaf corresponding to this suffix. Now, because all these dollar symbols are different, there's no way that this $2 symbol occurs in any other part in the text. So this leaf will be a branch on its own. At the very latest, when this $2 comes along, it's an edge that is only once there, and you will never have anything else occurring there. There's no way to have that shared. So these dollar edges always lead to a leaf. That's what this here says, and that means conceptually I can ignore that this suffix contains a copy of all the later texts. As soon as I have a unique leaf here, I could say that leaf corresponds to the jth text and the ith position in that text. So there's a little bit of doing arithmetic back and forth from the coordinates in the global text to the local text, but you just subtract all the lengths of those before it. We'll see an example in a second, but in a way, what you should take from this slide is there's a simple way to generalize the suffix tree so that the same is true as before. We have a compact trie of the suffixes of all the texts in the tree. And now the leaves don't just tell me where the suffix starts, but they also tell me which of the texts it was. That's what I conceptually want from this generalized suffix tree. And algorithmically, it works by just doing a standard suffix tree on this artificial text, concatenating everything with special symbols in between. Before I move on to the example, time to wake you up with a little question. This one's not a trick question. It's just about being sure that we have the same definition in mind. And then you also know what the answer should be when we look at the example. Right, we almost have our 50 people together. By the time I switch, I guess we have it. Yeah, vast majority is the same opinion. There's always these word pictures make it look like, oh, there's a few people put BCA, but it's actually 50 votes for BCA. And that's of course also the right answer. Because this last string is so short, there's really not much else we can do unless we can fit the entire string of length 4 into the others, which we cannot. The longest common substring can have length 3, right? And so because BCA occurs in all 3, and the first even twice, that's the answer. Now, how can we find this algorithmically? It is similar to the longest repeated string, but there are two changes. One is we have to use the generalized suffix tree because we have different texts. And the second is we're not happy if the text just occurs twice anywhere. It should somehow occur so that it occurs in each of the texts. That's a second constraint. And we can check both of these. So the algorithm works as follows. It computes the generalized suffix tree for our collection of texts. Then we compute the string depths in the second step, same as before. Another thing we compute is the subset of texts that have a leaf below a certain internal node. So here's how to do this in a bottom-up traversal, but just to explain what this this label, this annotation should mean. Every internal node or every node in general has a set of indices of texts so that there's some way to run through that node with a suffix of that text, which also means the path from the root to that node occurs in that text. And you just compute for every node which texts does that occur in. I'll show an example, then I guess it's much clearer. But let's first look at the running time. So this here is this is order n for the size of the generalized text, but the size of the generalized text is just the text is the concatenation, so the size is the sum of the sizes. I guess plus k, but we assume that the texts are not empty, so in terms of big O, that's the same. For that second step, if we look at how it is implemented as a traversal, you can do a bottom-up traversal. This is, again, we haven't discussed depth-first search and tree traversal in detail in this module, but you'll either do it next year or you've done it in the Python module. So there's a recursive function. You start at the root, and then you recurse to all children. And bottom-up traversal means you do something after, you do something coming back. So when you reach a leaf, you know this because you don't recurse further. Then if you have a leaf, ji meant its starting position I in text tj. And so we just put the singleton set j, a leaf of that type corresponds to just the text j. If I come back up from the recursion and I have computed those sets for all my children, I can now compute the set for myself for this internal node by taking the union of all those sets. And if you do this in that way as a recursive procedure, its time is linear in the number of nodes in the suffix tree, and that's again overall order n time because we have order n nodes in the suffix tree. The computation of the string depths is like before. That hasn't changed. It's just using the generalized suffix tree, but it looks for that computation the same as an ordinary suffix tree. And the last step is also the same, except that we have to check this additional constraint. So we want to find a node that has largest string depth, the longest repeated thing, but we only include those internal nodes where we have the full set of all texts, where the set of indices of texts that have a leaf below them is the entire set 1 up to k. And here's the promised example. It looks a bit wild maybe because it's a larger text. That's the generalized suffix tree for these 3 example strings. So you see, let's take example, for example, CA and then $2. There must be a path for this because it's a suffix of the second string. So if I go down with BC, CA, and then $2 brings me to this leaf, and that's the leaf that corresponds to that suffix. And similarly, you can do it for all the others. Now I've already put the string depth in the nodes, which, by the way, if you represent the suffix tree as a compact trie, the numbers in the nodes that we need anyways for the trie is also the string depth. I don't know if you made that connection already, but they are really the same. So when the algorithm says compute the string depth, it actually doesn't have to do anything. The representation of the suffix tree would already know that number. It's just on the human version that we didn't show them. The green numbers we still have to compute. So let's look at an example there as well. For completeness, every leaf would have a green number that corresponds to the $, that is at its end. So this is a leaf that corresponds to a substring from, or a suffix from text 2. This is a leaf that corresponds to a suffix from text 1. That means this internal node corresponds to a repeated string. So ABCA is a string that occurs in both text 1 and text 2. Let's double check that. A, B, C, A. I can find that here, and I can find that here. Okay. It does not occur in text 3. That's why this is only 1 and 2 and not also index 3. Another example, this one here, there's a leaf that corresponds to text 3 and 2. So this corresponds to 2 and 3, but not 1. And the path down here is AA. So indeed, there's AA in this and AA in this text, but there's no repeated A in the first text. Okay, so you see how this is going. The bottom-up traversal is then just annotate all the leaves, and for every internal node, take the union of the sets at the children. Now, from all those nodes that really have all 3, which are just these, we now have to pick the one with maximal string depth. And in this case, that's clearly this one. It's the only one with 3 that is circled in blue. And that corresponds to the string BCA that you identified in the question before. Okay? Yeah, I wonder if starting with the example would have made this clearer. Maybe I'll swap it around. So let's wrap up. We learned 2 things. We learned there's a generalized suffix tree, so you can essentially treat it conceptually as having the same kind of structure as a normal one, but it also remembers the suffix of what text are we talking about. And you can get that for free. Second trick we learned, we can do some extra annotations in the tree. We can get the string depth of a node, so the number of characters on the path to that node. We can get that for free with the linear time extra pre-processing. And we can do things like this, find the set of all indices of texts that are below a certain node. We can also do that in a linear time pre-processing. Does someone still need the attendance code? There were a few questions on Slido. Let me briefly go there. One was the question, network in the room is lagging. That's on Slido, I suppose. I noticed on my phone as well that it's slow. My suspicion is that it's mostly EduRoam, or I'm not even on EduRoam. Might just be well-isolated Faraday cage. Hope the recording and so on is fine. Yeah, it's the usual warning from YouTube, but the stream has always been okay despite that. Anyways, there's not really anything I can do, but the local recording is kind of safe. Then there was this question about extending the deadline. I don't want to arbitrarily extend deadlines if not needed. If you're specifically talking about the time, I extended it last time because it was a Thursday, and so it was essentially right after this lecture, which struck me as a bit unfortunate for myself. So officially 6 p.m. I'm already leaning out of the window. The uni says after 5 p.m. you can't have deadlines because students are supposed to have free time. I never quite understood that argument, because giving you more time, you can still finish at 5 p.m. I'm fine with that. I mean, if you care a lot, we can push it to midnight the same day, but I don't want to push it further, otherwise it affects marking deadlines and so on. So I mean, Saturday I would avoid. We could do 23:59 as a compromise. I don't know if someone wants to comment if there's a specific thing where this is helpful. Right, so I mean, you're rushing well ahead. There's no resit for these continuous assessments normally. Instead, there's the resit exam, Now you haven't even done your first exam. So first you have to fail your exam, then you can go for the resit. Of course, that's not the plan, right? The exam is in January. I think there's a draft date, but it's not final yet. So at the moment, it's planned for January 18, but you can't rely on it. It might move, and you will be told next week, I think. The official release of the exam schedule is next week. So it should be... The release is on 5th? Yeah, that is next week. Yeah. Yeah, so you'll know for sure, and we all know for sure next week. And then the resit, I mean, if you have to, because you failed the main exam, you wouldn't normally otherwise have to go to a resit. If you fail the main exam, you take the resit in August. So long time to go. Okay, yeah, midnight's fine. Well, 23:59 has to be still tomorrow. UK time. Computer science conferences tend to have this a day for the deadline and then anywhere on Earth. So as long as it's that day someplace on the planet, it still counts, which usually means around here it's midday the next day. I'm not doing that, so local time, okay. We're not spread across time zones too much. Yeah, August is definitely the resit period for that. I think 3 people got 100, so it was definitely possible. We had the full spread pretty much. So in a way you can say successful marking scheme because it used the entire marking range naturally. I was a bit late with putting in the extensions for exemptions from late penalty. I only put them in today. So if you have one and your mark fell off, check again if it's fixed now. All right, back to suffix trees and a few more applications. Okay. In the next subsection, we'll see a few more applications of suffix trees. In a way, we've just done the warm-up so far. The real power of suffix trees comes with this additional trick that they make possible. And that enables a few more applications where, again, if you see them first, it looks like this can't be possible in that linear time. But this makes it possible, these longest common extensions. I'll explain what that is in a second. So we've already made use of that implicitly without me telling you and without you noticing probably. But you can formalize the following problem on a string, the longest common extension problem. You're given a string. Now the deal is that you get this string up front as in string indexing. So you can do pre-processing on this text. And then later I'll ask you LCE queries, longest common extension queries, which means I'll give you 2 positions in that text. One here, one there. And you have to tell me how many characters can I read from there to the right that match. So how far can I read the same characters here that are equal? And all I want to know is how many characters, so not the actual text. That's the formal definition here. The LCE query for I and j is the largest L, so that if I read from I and from j for L characters, I get the same string. And because it's the largest L, it means if you take one more character, there's a mismatch. So the next one would be a different character at the 2 places. And you see how this is connected to what we've done before in terms of the longest common prefix of suffixes. Indeed, it's the very same thing. If I ask for the longest common extension at 2 positions, I could also say I ask for the suffixes starting at these two positions and how many characters they have in common. So that's really just a different name for the same thing. So let me draw my favorite picture again. I can take this TI, and I can take TJ, which starts here, and align it below TI and TJ. And then I can ask how many characters here are equal before I get a mismatch. So these two things are the same, just a different name. And we've also already seen the second equation, which relates this to the suffix tree, namely the longest common prefix of any two suffixes. So any two suffixes corresponds to some leaves in the suffix tree. And then I can find the lowest common ancestor of those two in the tree, and that will give me the string depth of that node will give me the longest common prefix of those suffixes. So if I take the lowest common ancestor of those two, it's a boring example because they have the root as the first thing where they join paths if you move upwards. So their longest common prefix is empty. They differ on the first character. And because this is banana ban, the entire thing, and this is naban, the first character is different. We've had the other example before with 5 and 7, where the lowest common ancestor was this node. So they had a longest common prefix of length 1. Okay, so you already know what I'm telling you here. It's just throwing in another piece of vocabulary in the mix, which is sometimes a bit more intuitive because it doesn't talk about suffixes. This observation, I mean, you can express this as this formal equation. I circled it because that's kind of a good one to memorize, just so you can quickly recover that fact, even if you don't remember. You would always have to draw an example and rediscover it. Otherwise, you can also memorize it. That's why I circled it again, but it's the same thing. So we defined a problem, okay? The problem being I give you the text, and later I'll ask you lots of these LCE queries, and you're supposed to tell me very fast how many characters these two places share. How can we solve that problem? There's different, more or less smart solutions. If I have the suffix tree already, I could use this last part and find the lowest common ancestor. So I could walk up from both nodes and keep checking if I found the same node. That's one option. Unfortunately, that's quite slow, at least in the worst case. If you imagine you're like in this, like for these two leaves, you're far away in the tree and you have to essentially walk all the way up to the root. Another option would be you pre-compute all those lowest common ancestors in one big table. But because you have n leaves, it would be for every pair of leaves an entry. So that's quadratic space. And even to just write that table to memory, you need quadratic time. So that's too slow on the pre-processing. There's another for LCE. If you use the other version of the problem, there's of course another solution that doesn't do any pre-processing, but instead at query time you're given these two positions, and so you keep walking to the right from both until there's a mismatch. So you just compute LCE naively at each query time. That is fast for the pre-processing because you do nothing. But at query time, you essentially have cost as much as the answer is. So if L is your answer, you would have cost of L. But in the worst case, that indeed is, again, linear. So it kind of gets you in the same ballpark as here. So both seems it's not so great. Now, without a further trick, you don't really get further, but there is another trick you can play. There's a way to compute for any two leaves in the suffix tree, their lowest common ancestor in constant time, after spending some pre-processing, but not this super slow quadratic time. Again, linear time is enough. So in a way, you can compute the suffix tree in linear time, and you can do this pre-processing for lowest common ancestors also in linear time. And then you can jump from any two leaves in one step, in constant time at least, to the lowest common ancestor. And if you do that, you can use the translation that LCA was the same as LCP was the same as LCE to compute longest common extensions in constant time. That's this box down here. So for the rest of this section, we'll use this as a black box. Now, this black box will also crack open. That will be the Christmas lecture. So I wanted to show you what is inside that black box, but I felt it's pushing a bit too far for exam materials, so that will be kind of just for your enjoyment. But that's Unit 9. So for now, that's also a promise. It'll be the last black box, I think, that I'll throw at you. For the moment, let's just take it as given and see what we can do with this. And the first application that uses this is something where we want to find approximate matches. So far, whenever we talked about string matching, we were interested in finding exact occurrences of the pattern in the text. There's many applications where it's desirable to allow little typos and so on, or a bit of noise. And the simplest version of that problem is the K mismatch matching problem. So similar to string matching, you're given a text and a pattern, but you're also given a bound on how many characters you're allowed to mess up and still call it a match. So formally, we say a match is some position of the text of the same length as the pattern, where the Hamming distance between that portion of the text and the pattern is at most k. So at most k characters are in mismatch. You've heard about Hamming distance when we talked about Hamming codes in Unit 6 in detail. So here it's just a reference back to that. But really it's k characters don't match. Okay. First, what are the simple solutions? You can take our good old brute force method for string matching and adapt it to this. The reason is the brute force method took every possible position in the text and said, let's see if I start here, can I find the pattern there? And you have this inner loop that just compares all the characters. Now in this inner loop, instead of comparing the characters and stopping as soon as you find any mismatch, you can keep going and count the number of mismatches in the same time. So at the same time as brute force string matching, you can also do this problem and determine all the matches where there's at most k mismatches. But if both your text and the pattern are fairly long, that's not so great. And we can do better. So we do a pre-processing on something like the generalized suffix tree again. We take the text, append some end of word marker, and then the pattern and a fresh end of word marker. And we use this this LCE data structure that I've just told you about as a black box. So we can find longest common extensions in this string in constant time. And that in particular means if I have my text and then the pattern afterwards, I can pick a position in the text and I can pick a position in the pattern. And in constant time, it tells me how many characters are aligned or how many characters are the same here. Okay? That's what we'll use. And for that, essentially what you need is the generalized suffix tree and all the string depths and the constant time lowest common ancestor, LCA data structure. But we'll just work with LCE for now. So any two positions you're given, you can find in constant time how many characters are the same. And with that, you can so you can use this simple algorithm that got called the kangaroo algorithm because it always does jumps. So how does it work? You have your text and your pattern. It has aspects of the naive string matching algorithm, the brute force algorithm, in that it goes through all positions in the text where the pattern could occur, so all guesses. So then we have a portion of the text, but now we're trying to speed up the matching to see whether or not there's at most k mismatches. So we count the number of mismatches. We have a position in the text and in the pattern. And as long as we haven't exceeded our budget of mismatches, we compute how many characters from this position in the text and the pattern match in one go. So starting from here, let me make the pattern a bit longer so that my kangaroo has more room to jump. So we start at this position, and now we ask how far can we jump, where what I jump over is characters that are equal. And that's the longest common extension of these two positions. It's the longest piece I can read from there to the right where all the characters are equal. Necessarily, one place after that will be a mismatch. Otherwise, we would have jumped further. So after jumping over these L characters, I go one more ahead. So I move forward by L plus 1. So I'm now standing right behind this mismatch. And I count, I've made one mistake so far. Then I jump again using another LCE until I find another mismatch. And then I'm standing right behind that. By doing this, I can do at most k steps, and no matter how long the pattern is, after time proportional to k, I know whether I found the end of the pattern. So I could match the entire pattern with at most k errors, or not, because I'm still in the middle of the pattern. I ran out of mismatch budget. So the algorithm is fairly simple. The only tricky bit is in the implementation of LCE, the black box for Christmas. So the overall time, instead of the brute force method, was n times m. We now brought this down to n times k. And k is a parameter that you give as a user. And usually k will be small. I mean, if you're trying to find a match because someone is searching something and they might make some typos, but if they've typed 20 characters wrong, then it's probably not a useful match anymore. But probably k is 2 or 3 or so. So this is essentially close to linear again, whereas this, if the pattern is long, might be substantially bigger. And we need this pre-processing, but that's n plus m. That's essentially, again, linear time. So for small k, this is a substantial improvement, and is also a practical algorithm. Now again, I often have these kind of extra sections, state of the art. Maybe I should at some point generally say, whenever it says state of the art, you can ignore it. That doesn't sound like a very, very helpful statement, but you don't need to know it for the exam. People pushed this further, so just in case you were wondering if that's best possible, it's not. You can play further algorithmic tricks, but I don't want to get into those. Right, so that's an application that doesn't even use suffix trees explicitly. They're only occurring inside this LCE query, hidden from you in that sense. The algorithm around it is fairly simple, but it gets the running time down substantially. And a last application is related to that. if you're trying to find patterns and you have a don't care character. So wildcard in this case, it's not like the star in the Unix shell where it can stand for an arbitrarily long string. It's a single character, but you don't care which one. You can do essentially the same as this kangaroo algorithm. A slight twist on that solves that version of the problem. And if you're still curious about more, I brought this book here as well that's on the slides. It's kind of the suffix tree Bible. There's a lot of more applications of suffix trees where if you try to solve it from first principles without using existing data structures, it seems it's very hard to solve efficiently. And with suffix trees potentially using this trick for lowest common ancestors, it's a relatively simple task to solve them. So the suffix tree in that sense really is this threshold invention that made a lot of other things very simple conceptually, and has lots of applications whenever you have these kind of strings, and the book focuses on biological sequences. So to wrap up, suffix trees are great from a theoretical perspective. They're linear time and space. You can construct them in time proportional to the length of the text. They use up space proportional to the length of the text, and made all these problems solvable, as I just said. From a practical perspective, there's still a few things that are kind of leaving wishes open. The original algorithms for constructing suffix trees, while there were linear time in theory, they were still relatively slow and also complicated to implement and to explain. And the suffix tree itself, because it's this tree with potentially many children and so on, it's a little less obvious how to represent it space efficiently. Think about it that way. We always assume in this section that the alphabet is finite and not crazy big, but it might be all ASCII characters, at least 26, or maybe all Latin characters, or all ASCII characters, 128 or 226. So it's in the dozens or hundreds. Now you have two options how to represent a node. You can represent a node with an array of child pointers. So it could be something like this. Then every node needs space sigma. If sigma is constant, that's linear space, but still it's a factor of a dozen or 100 overhead. The other option would be some other data structure within each little node that tells you what child pointers exist. So you could have, for example, a little binary search tree over the labels, and then it's a little dictionary in each node that maps from the edge label to the child pointer. But then you have a log sigma space overhead for each traversal, because that's the binary search tree. So here you have a sigma space overhead. Here you have a log sigma time overhead. It's just not clear. I mean, both is maybe fine, but if sigma is not tiny, it's both are not negligible. And even this version still has a lot of pointers. So it's in a way as great as is from a theoretical perspective, but if you implement it, it's still not as good as one would hope. Before we move on, I guess it's time for a break. So the next section we'll try to attack this leftover overhead.
I asked you about the question, the test question on campus wire as well.
Right.
This particular question, right? So I am getting up till here, and I understand how the C is coming, but I don't get how the B is coming. Because in the last comparison, I'm comparing C and B, and I'm not comparing B.
Right, so the way the algorithm works, you always have the dictionary up to this point, and now you're looking for the longest match that you can find from what's missing. So if we agree up to this point after BBCA, so what's left to encode is C and B. Now the question at that point is, what's the longest phrase in the dictionary that starts with C or CB? There's only these two, so either the question just becomes, is CB part of the dictionary?
No, CB is not part of the dictionary. I'm adding CB altogether to the dictionary, right?
But only after the encoding.
Yeah, but
that's what I said on CampusWire. What you're supposed to give as answer is the phrase that you encode, not the phrase that goes into the dictionary. It is a different.
It's this, right? This is what I'm encoding the numbers with. This is going, and CB I got it as 3.
So what's the dictionary? How do you?
The entries which I'm doing.
Okay.
After CB, I don't have anything. After CB.
Right. Where's CB in your dictionary?
It is not there.
Right.
The last one is CB, and it starts with C. I'm encoding it as 3, which means C.
So what you should enter in the box is basically going through this.
Yeah.
And just list what's the code word corresponding to those.
Yeah, that's what I did, but I stopped at C, but I'm not getting B after this.
I see. Well, you still have to encode B, right? So you added CB to the dictionary, but you've only encoded the C, so you still have to start another round where you now you can only encode B with what you have because it's a single character. But in principle, it just goes one more round.
If I'm adding B as a single character, that doesn't mean I mean I shouldn't be adding BB here, right? Because I added BB, so because B is already there in the entry.
You're mixing up what you encode and what you add to the dictionary.
Yeah.
After this one, you've encoded the A, the C, but there's still a B left from the text. You have to send this to the other person to decode it.
Comparing B with the blank space.
You're stuck with B. You're left with B. So you find the longest phrase in the dictionary that you can find at this point, and that's B. I'm not sure what you mean by comparing. I mean, in case of doubt, look at the slides and go through the algorithm step by step, right? It tells you pretty much that each step.
I worked it over.
Okay.
In this particular case, if I'm doing it for just one round, I'm getting this. But when I'm continuing, I'm getting higher numbers than what is required. Although the test is asking for 4 rounds. And I don't get how 35 is there after 37. Shouldn't be increased because there is 1 after 37.
Well, that's if you follow the algorithm, it can happen. Each round adds 2 numbers, but the range that you add up by that is different. So because this one reaches one further to the left, it might reach another large number that the last entry doesn't reach.
Yeah, exactly. It keeps on increasing, right? Because all are positive numbers, it doesn't decrease.
Yeah, but you're adding up different sets of numbers. The position for 1 is 1 shift to the left, so it adds a number in that's further to the left, and the last position doesn't get that number, so it could be smaller, like in this case.
Do you mind explaining this again?
Well, I mean, can you explain what you did in one round here?
The first round I'm adding 2 plus 2 and carrying 2 plus 2 4 4 0 4 plus
Hold on.
6 10.
This one is what? Is a 4.
Yeah.
But you're adding 2 and 0.
Oh no, I'm adding 4 and 0.
Nope. You always take the two numbers from the previous round and add those up.
Oh, you said in the lectures if there is a 0, you carry the same number forward.
Well, that's what happens here, right? 2 and 0 is still 2. What I said was true about the final result after you computed the full prefix sums. But here you're stopping the algorithm early. Yeah, have a look at the algorithm specifically. You have to follow the precise description of the algorithm. Okay. So I think we have to continue. Shall we do it after the section?
So I'll just take a little of the time. So suppose here's my score in the CA1. So will it be like a resit in the exam or like?
No, the continuous assessment doesn't need to be reset if you overall pass, because it's a small percentage. What mostly counts is the exam, because that's 60%.
Main exam.
The main exam. There's only one exam.
February or January?
January.
Okay.
Yeah,
Means I have to work hard for it. Because
of course.
that's the only way left. So this 45 out of 100 is a failed score.
It's compensatable fail because it's between 45 and 50. But yeah,
So since I've got this much, I have to like redo this assignment and submit.
No.
Or
no. The individual continuous assessments, there's no resets for those.
taken, if it's counted, so how much? The 100 marks. So all the 100 marks will be taken.
Let me talk you through it after the lecture.
Okay.
Or you can also ask the student experience team to do counterfactuals with you. I mean,
Anyway, that's all right, but I'll work for the real exam.
sure, that's the most important bit because it counts the most.
This is it like it's not related to the incident in the exam, right?
No. The reset is for the entire module for all failed components.
This means I haven't failed in the entire module.
No, not yet. I mean, this is only 10%.
I was like scared.
Yeah, not yet. No, the main thing is to pass the exam.
Okay, thank
That's the most important bit. Yep.
About the assignment 2, and I already.
Let's do it after this section.
I mean, I can deliver twice. Can I?
You can submit it. You can resubmit. Is that what you mean?
Okay, thank you.
Yeah. You can. We always just take the latest, the newest submission as the final one. I've seen there's also questions on Slido, but let me first do that part of suffix arrays, and then we can come back to those. In the next subsection, we'll look at suffix arrays. Sounds similar to suffix trees and has relations, but first of all, looks like an entirely different beast. The ultimate goal will be to put our suffix trees on a diet by getting rid of most of the pointers. So here's our suffix tree, the way I've drawn it before in some examples, growing to the side. And what I've done here is put the leaves one below the other. I didn't stress this earlier, but we've actually had that before. If you make sure that all the child edges from each node are ordered by the alphabetic order of the letters, then you actually get all those suffixes in lexicographic order. The dollar comes first because that's always the smallest character in our ordering. Then there's a node with A, so everything that starts with an A will be in the range of that subtree. And that comes before everything that starts with a B, which is in this subtree, and so on. All right, so there's an inherent connection between suffix trees and ordering the suffixes or sorting all the suffixes in the standard lexicographic order, at least if you draw the child edges in the right order. And so how about forgetting about this fancy tree with all its pointers and just keeping that sorted order? Sounds maybe a bit crazy because we've used a lot from the tree structure in these applications. But let's see how far we get. I'll call this L for leaves. So you should think of it basically as L of 0 is the index for this leaf, which always is the last. So in banana ban would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Hope that's correct. L0 would be 9 because the first leaf in lexicographic order is the leaf that has starting index 9 and so on. So you can represent this lexicographic ordering as just an array of numbers. Now, it turns out that's enough to do some of the questions, to answer some of the questions that we've answered before with the suffix tree. For example, we can still do string matching. If I have a pattern like Anna, how do I find the occurrences of that pattern in our text? I do a binary search in this sorted list. So how would binary search work? Well, we'd start in the middle. Now I would compare, is Anna smaller or bigger than this in alphabetic order? And okay, we straight bang into the special case. It depends now what I add to Anna at the end. Let's suppose I add the $sign. Then it would be smaller. So now instead of the whole range, I have this as the range of possibilities for the binary search. I compare it with the middle one. A and $ is smaller. So now I'm in this range. And I would do another example, another comparison here. So I would find that if Anna $ was in this list, it would go between those two. I could do a second, I don't know, Anna pound, where pound is bigger than all dollars. Of course, pound's bigger than dollars. If you do this binary search again, you would find that it should go in between here. What does that mean? It means all the words that start with Anna are between those two positions. And if I look in my array, what the numbers there are in this L array, it would be the starting indices of these suffixes, which is nothing but the occurrences, the first index of the occurrence of Anna. So by two binary searches, I can find all the indices where this string occurs. So I could do the same kind of trick as in the suffix tree, but without all the tree. I've not looked at all that stuff. I've forgotten all the pointers and all of the nodes. I just kept the sorted order of the suffixes. So that's a bit of my motivation for why you don't actually need much from the suffix tree for this application. So formally, the suffix array is just this list of indices, one array of numbers. I've explained this already, but here it's listed again. Note that it has indices from 0 up to n inclusive, because we add this $ symbol, so we have n+1 characters in the text, right? Same as before. And yeah, to say it again, so the rth entry in the suffix array is the rth smallest suffix in lexicographic order. And what we have in the array is the starting index of that suffix. The algorithm that I sketched on the example for finding the occurrences of a pattern, it does two binary searches. Now you will remember binary search takes log n plus 2 if we want to be worst case on the safe side. Steps of recursing down until you found a position. But each of the comparisons can take up to m character comparisons. So the overall time is log n times m. Okay? And you should compare this. In the suffix tree, we had essentially m as our matching time. So we have a log n overhead, which comes from forgetting all of the tree. So in a way, I mean, it's not nothing, but log n is much, much smaller than n. So you could say that's tolerable to be a bit slower when now all you need is just an array of numbers and not this dozens times larger suffix tree. So as a first step, that already looks promising. And what I'll convince you in the rest of this unit is you can base on this suffix array, you can base all the algorithms that we've seen for suffix trees with a few extra tricks. You can simulate what they do with much less memory. Okay, there's a few nitpicks on the definitions that I'd like to hammer in. So as soon as this works. Yep, it's come up now. I'll leave it here, then you have the nice rendering. Actually, you can see the question. Maybe it's useful to keep that slide up, then you have the definitions there. I don't want to rush this question because there's a lot of insight to be had from that one. So take your time. Oh, we reached my magic threshold of 50 people. And we're still busy thinking. A few. Okay, let me start discussing so we don't overrun too badly. It's actually a lot of stuff is correct on this one. Okay, let's see. First of all, L lists the start indices of the leaves, or the start indices of the suffixes corresponding to the leaves in left to right order if we draw the tree in the normal way, where smaller goes to the left and larger goes to the right for each child. In my upside down world here, you have to kind of tilt your head to the left. Otherwise, this is correct. The path label here, it's not the leaf storing R, but it's the rth smallest leaf, or lexicographic order. So it's kind of the other way around, and this one is the right answer. Another way to say that same thing is if you take the suffix that starts at position L of R, then that's the rth smallest among those. The last is maybe, I don't know, maybe a bit surprising, but I think I've said it quite explicitly. Both the suffix array and the suffix tree take, under the assumption that the alphabet is constant, take a linear amount of space, theta of n words of space. But the constant for the suffix tree will be much bigger. And indeed, for the suffix array, the alphabet doesn't even make a difference. All that I'm storing is n numbers, n indices between 0 and n. So for the suffix array, the alphabet size is irrelevant, and for the suffix tree, that certainly plays a role. Right, and we've just seen both can be used to solve string text indexing or string matching. Text indexing is the same as string matching, but with the pre-processing on the text explicitly allowed. Okay. Maybe apart from the last question, most people agreed on this. So maybe it was just maybe it should have said string matching to be more clear. Now we've seen this suffix array could be useful, but how do we get it? That we still have to find out. One option is compute the suffix tree and then read off the order of the leaves. But we're trying to avoid to have these complicated construction algorithms for the suffix tree. So it would be a bit disappointing if we had to construct the tree as an intermediate step. Instead, we can go more directly by the definition. The suffix array needs all the suffixes in sorted order, so we might as well produce that by sorting. And we could just use any of the general purpose sorting methods. Unit 3 says hi. That's trivial to code up. You just have a comparison functions for strings. That's usually built into libraries anyways. So this takes 2 lines of code. Unfortunately, this is not so great because the comparison of any 2 suffixes could take a linear time. As often, if you take a boring text like everything is A's, that gives you the worst case for this stupid algorithm. If you're not careful, then that extreme case for a text will usually screw you over. And so while it's easy to code, it's worse than quadratic in the worst case. So that's not quite so great. And indeed, we can do better. We can do even better without going very far into the world of suffixes. The first thing I want to show you is just a general purpose method to sort strings. That's better than that, at least on average. Before we get to that, another short connection that it's worth making. This time it's unit 5 that says hi. That was the Burrs-Wheeler transform. And it's worth pointing out So in case of doubt, I wanna point out this says very easily, so it should be a trivial algorithm, both fast and conceptually super easy. That's important here because if you strike that out, it's possible either way by just computing it from scratch. But that's not the what the question is getting at. We passed the magic 50. So there's a roughly equal, not evil, split between options 2 and 3. Where now things shift. Okay. Anyways, the majority is right. So here, it's true that you can compute the Burrs-Wheeler transform from the suffix array or from the suffix tree. The reason for that is if you have, let me show you the connection. So this is a slide I just borrowed back from Unit 5. Remember what the Burrs-Wheeler transform was doing is it takes all the cyclic shifts and sorts them. And then it takes this last column, that was the BWT. And to compute that, note when we do the sorting, we never have to look past the dollar symbol because the dollar symbol in all of the cyclic shifts occurs at a different position. So there's no way we'll ever get with our comparisons behind that. We would only get behind that symbol if there was the same dollar symbol in both strings that we're comparing. But that can never happen here. So in a way, sorting these cyclic shifts is the same as sorting just the suffixes. You don't see the slides. Didn't switch back in. That was what you were supposed to see. The Burrs-Wheeler transform takes all the cyclic shifts, sorts those, and takes the last column. That's exactly the slide from back then. And if you compare any of the two cyclic shifts, then you always stop comparing at the dollar symbol or earlier. You never go further because the dollar symbol is never aligned at the same position. And so sorting these cyclic shifts is the same as sorting the suffixes. The order will be exactly the same. And so if we have all the suffixes sorted, how do we get the BWT? The formal connection is here. I can take the position that is in the corresponding entry of the suffix array. And now I would want, instead of the starting index, I want the letter that is wrapped around and in the last column. That is actually the character that comes one before that character. So what I have to do is I subtract one and then look in the string or in the text. Maybe it should be, okay, so it was called the source text in Unit 5. So you look at the position that comes before that starting position of the suffix. That's how you can compute the Burrs-Wheeler transform in linear time from the suffix array. Now, the other direction seems unclear. Just because you have these characters, it's not, at least not very easy to figure out what the order of the suffixes should be. Okay. Yeah, I want to briefly show this sorting algorithm. There's no code, it's just an example, so we can go over this fairly quickly. It's not the most central thing. I just want to show before we go to the more sophisticated algorithm tomorrow. For many cases, you get with a simpler solution a fair bit. So think about the general problem. You're given a list of strings like these. How would you sort them efficiently? What's not so great an idea is to use comparison-based sorting say merge sort or quick sort as a black box. And whenever you need to compare two strings, you just do the comparison from start to beginning to the end. The reason that's not so great is if the strings agree on a long common prefix, you repeatedly scan that long common prefix, and you pay for that each time whenever you do a comparison. So the extreme case is, suppose all the strings start with some long prefix that is the same for all strings, and then they differ. Say you're sorting URLs and they're all within the university domain, then you would have that easily. And so there's an easy way to do better than that. And that is based on quicksort, but it takes advantage of the fact that we're sorting strings. And it works like this. We pick a pivot element as always in quicksort, but we'll only look at the first character in this round. That's why these are highlighted. So the pivot character tells us there's words that start with a character smaller than this character, and those that start with a letter larger than that character, and those that start with that character. That's why it's called fat pivot, because there's a partition that has everything that's equal to the pivot according to the first character. Right? These have a starting character smaller than s, these larger than s, and these have s. Now the trick is, for all those that start with an s, I know that they all start with an s, so no need to look at that s ever again. Instead, I'll just remember for these strings, the first character is definitely the same. Start looking at the second. That's the main trick. The way the example would continue, here you pick a pivot. Okay, it's this tiny example, so you just have these two sorted. Here it's more interesting. The pivot says I have h as the second character, so I split by the second character into those that have a character before h and after h, and those that have h. And again, for those that have an h as the second character, I know they have sh as the first two characters for all of them. Never look at them again. Okay? In the last example, we have the degenerate case that they are all equal. So I just read over all the t's, never look at them again. And there's no strings that have a smaller or larger character. These are done. These are sub-problems of size 1. For these, I pick another pivot, and I again have this degenerate case. They all have the same next character. So I just advance and never look at the e again. For these, I have some, excuse me, some that are smaller. No, these all have e and one that's larger. So again, I never look at the e again. And here I just advance one more because the algorithm doesn't see it yet, but of course the strings are just the same. One more round here. Okay, L, I have 2 that start with L and 3 that are smaller. I guess you see how this continues. Now the trick with all of those, okay, these continue for a while until they discover that indeed the two strings are the same. But if you analyze this globally, you never read for two strings if they have some shared prefix. You never read that shared prefix twice. You only read it once. Because you always remember, if you go into this middle round, this middle partition, you remember that they were the same. So when you discovered once that two strings have a common prefix, you're not going to look at it again. That's fat pivot radix quicksort. If you want to see the details and code and so on in more slow pace, it's in the red book that we used for other units. I'll skip the details for the code here, so you don't need to know that part. You can show that if the texts are somewhat random, this is a very fast method. It's also very simple to code and works well for many types of texts. It's still fairly slow if your text is completely degenerate. If your text is all A's, you would always have this middle partition, and you would read through the entire text, so it would be quadratic still. But you've reduced it for many more interesting cases where it's not suffixes of a text. This is a good method. Now, for the concrete case that we're concerned with, sorting the suffixes of a fixed text, we can do much better even in the worst case. And for that, we'll have to work a bit harder. And we won't do that tonight, but that's what's coming up. All right. Very quick one for the questions. Right, I won't do that again now. We'll watch the recordings, then you can see what I said again. But of course, ask on Campus Wire. So that's kind of lost in the abstraction. A no and a yes both take one bit. So this honking, suppose the honking is either one long or one very short one, and they both take the same time. And so it doesn't matter whether you send a yes or a no. It's supposed to be symmetric in that sense. Look at the formalization, not just this fluffy story. The formalization answers that question as well. Okay, see you tomorrow.